So honestly, guys, this video hopefully will be a little bit easier than those dot diagrams. Those are a real hassle. And what we're really interested in at the end of the day is coming up with Lewis structures. Okay, so a Lewis structure, you're going to see single bonds, you're going to see double bonds, and triple bonds. Okay, so single, double, and triple bonds. Single bonds are two shared electrons. Double bonds, 4 shared electrons. And triple bonds, 6 shared electrons. Okay, now we're also going to learn about lone pairs. Lone pairs of electrons. Electrons come in pairs, right? We learned that you can have an upspin electron or a downspin electron in orbitals. And so lone pairs represent an upspin and a downspin electron in a given orbital. But lone pairs aren't bonds. They belong only to a single atom. They're not the bonding ones, okay? So sometimes we call these bonds over here, these types of things, these are called bonding pairs. And that's in contrast with lone pairs, okay? So you've got bonding pairs and then lone pairs. All right, now that didn't work out so well. Come on. Okay. Get that all red. Boom. Okay, so we're going to go through these steps, and I just think it's easier if at first I work through some simple examples so you can learn the steps as we go along instead of just reading through a bunch of steps. But let's start off with a simple one like we did in the dot diagrams, a similar one. Do you remember your diatomic elements? There's 7 of them. Iodine is one of the diatomic elements. And so iodine, we're going to figure out the Lewis structure for the iodine molecule. Okay, so for iodine, the first step is to examine the formula and count up all the valence electrons from all the atoms. Okay, now in iodine, we've got 2 iodine atoms. Each iodine has 7 valence electrons because this is in group 7A. It allows you to know you've got 7 valence electrons. Okay, so how many total valence electrons is that? That's going to be 2 times 7. So we're going to have 14 valence electrons total in the structure. And they're either going to be bonding pairs or lone pairs. Okay, so 14 valence electrons. We're not doing an ion, okay? Iodide is a neutral, iodine is a neutral molecule. So there's no charge written up here, right? The charge is like 0. We didn't even write it. So we don't have to worry about that step. But I'll show you an example in a minute. Attach all the atoms with single bonds, okay? So 2 iodine atoms, we got to attach them with a single bond. So I've connected them with a line. That's the single bond. Now, in molecules with more than 2 atoms, there will be a central atom. So not in this example, but in a minute we'll have to kind of think through how to decide which one might be the central atom. Okay, step 3 for us. Subtract the number of electrons you've used up from the original number. Well, this has 2 electrons. It's a single bond. So I'm going to subtract that number of electrons from the total. This is just to help me keep track of how many I have. So I'm going to draw the single bond in this red color, and that's 2 electrons. So I'm going to subtract 2, and that leaves 12 electrons left. Okay, 14 minus 2 is 12 remaining valence electrons. Okay, I just used up 2 right here. 12 more. Place the remaining electrons as lone pairs on the atoms, attempting to satisfy the octet rule. Okay, so they need to be lone pairs, and right here, lone pairs, and we're going to attempt to satisfy the octet rule. So I have 12 electrons, and I'm going to try to make sure every atom has an octet over here. So 2, 4, 6. I got to group them up as pairs. 2, 4, 6, 8, 10, 12. Okay? When I added 6 electrons to that iodine, those 6 plus the 2 here in red, that bond is 2 electrons, that makes 8 electrons. That's 8 electrons right there. Okay? So that iodine atom has an octet. This one is kind of the same. It's also got an octet. And so we have satisfied the octet rule, and we've used up all the electrons. There's no more electrons left. And so what that means is our structure is a valid Lewis structure. And so I would just simply draw it, without the different colors. This is what its structure would look like. Okay, so that's the Lewis structure for iodine. And we don't have to go through the other steps. The other steps involve making double and triple bonds. Okay, so if every atom still does not have an octet after what we just did, then there's some extra steps. Okay, so let's move on and do another one. Okay, so let's try carbon monoxide. Carbon monoxide. Okay, so in carbon monoxide, each carbon brings 4 electrons from its valence sublevels, and each oxygen brings 6, because carbon is in group 4A, oxygen is in group 6A, so those are the number of valence electrons. We've got 10 valence electrons. We're going to connect the first atoms with a single bond. Okay, so that's like step 2 up here. Okay, and we still don't need to worry about the central atom. We've used 2 electrons here, so I'm going to subtract 2. I've got 8 more electrons to place. I'm going to try now to satisfy the octet rule by placing these electrons as lone pairs. Okay, so it doesn't really matter where I start, but I've got 8 electrons I can place. So 2, 4, 6. Now that carbon atom has an octet, but I've got 2 more electrons left, so I'm going to put them over here. But that's all the electrons I'm allowed to place. And notice we don't have an octet. So what do? We're kind of stuck, right? If every atom still does not have an octet, we're going to move around lone pairs and make them bonding pairs. Okay, an atom already with an octet can share its lone pair electrons and still keep its octet. And that's going to create double or triple bonds. Okay, so this carbon atom, you can see it already has an octet. But the oxygen atom doesn't. It only has 6 electrons, and it's going to need 4 electrons, and it's going to need 4 more. Okay, so how can it do that? Well, these electrons right here, we're going to scoot them in, and those are going to become a double bond. Okay, so when that happens, now we've got this situation, which is a little bit better. Carbon still has its octet, because all we did was share, right? When you share, you don't actually lose anything, in a sense. So carbon still has its octet. Oxygen's doing a little bit better now. It's got 6 electrons. Okay, so let's do that one more time and scoot that lone pair. Can scoot that lone pair in. And now we're going to get a triple bond. Carbon to oxygen with lone pairs on each atom. okay? And by the way, it doesn't really matter where you put the lone pairs. At first they were up here. It's totally fine to scoot them, off to the side. So that's what I'll do, okay? And there is the Lewis structure for carbon monoxide. So we have a triple bond, and the carbon atom has a lone pair, the oxygen atom has a lone pair. And let's verify that this is valid. Okay, this is important. It's going to be a valid structure if you have two conditions that are satisfied. So, do you have the right number of valence electrons in the structure? Remember that total number of valence electrons, which was 10 from the beginning, 4 from carbon, and 6 from oxygen. So there should be 10 electrons in here. So let's count them up. Do we have 10? Here's 2, 4, oh goodness, highlight's too big. 2, 4, 6, 8, 10. So we've got 10 valence electrons in there. That's good. All right. Now the other condition that we need to satisfy is, does each atom have an octet? Okay. Now, something important, hydrogen gets a duet. Okay, but all the other nonmetals are going to have an octet. So, does each atom have an octet? Well, that's what we were working towards up here, trying to make sure that each atom has an octet. And there we can see that this carbon still has 8 electrons, 8 valence electrons, and the oxygen now has 8 valence electrons. So that is a valid Lewis structure. Okay, so you don't have to do all that circling and stuff on your work. If you just gave me this right here, that's it. That's the valid structure for carbon monoxide. Now, one final one to attempt today. Together. Remember carbon dioxide from the other video? That was kind of tough figuring out. But following this method should be kind of simple. Okay, let's count up all of the electrons, all the valence electrons total. Carbon brings 4, it's in group 4A. I've got 2 oxygen atoms, and each of them brings 6 valence electrons. They're in group 6A. So we've got 4 plus 12. That's 16 valence electrons total. Okay, now at this point, we're going to attach the atoms with single bonds, and we have more than 2 atoms. So we need to figure out what a central atom is going to be. The atom that can form the most bonds should be placed in the center. Okay, so how can we decide which atom between carbon or oxygen can form the most bonds? That's the one we should place in the center. We'll have a look at the periodic table here for a second. And I'm going to erase all this business. Okay, so our 2 elements for this molecule are carbon and oxygen. Now, which of these could form the most bonds? Okay, well, bonds form every time you get another electron from some other atom. And carbon needs to get 4 more electrons. 1, 2, 3, 4 more electrons before it gets an octet, right? Remember, carbon, it's a orbital diagram. Looks something like this. It needs, it needs 4 more electrons, right? It needs like 2 here, right? It needs 4 more electrons. It could form up to 4 bonds. Okay, well, really it needs 4 more electrons. Okay, whereas oxygen, it only needs 2 more electrons. before it becomes stable like neon. Okay? And so oxygen only needs 2 electrons. Okay, so carbon could form more bonds because it needs more electrons. So it can form more bonds. Okay, so let's go back to our structure. Because carbon can form more bonds, we're going to place it in the center. And now we're going to attach the atoms with single bonds. So it doesn't really matter how you draw it. We're just going to attach the atoms with single bonds. There's the carbon and the 2 oxygens. We've used up 2 plus 4 electrons. We've got 12 more electrons to place. I'm going to try to satisfy the octet rule. Let's start in the middle, because carbon, we can give it an octet really quick. There's 2, 4, 6, 8, 10, 12. That's all the electrons I'm allowed to place. Carbon currently has an octet, but the oxygens don't. 6 electrons there, 6 electrons there. The carbon is fine. Oh, 8, excuse me, 8. Okay, so the one that has the octet is totally free to share, right? Those lone pairs can become bonding pairs. So let's scoot those in. That lone pair could go there, that lone pair could go there. And what does that give us? Now we've got double bonds, and each oxygen atom has 2 lone pairs. So let's double check our structure. There should be 16 total electrons in there. We've got 2, 4, 6, 8, 10, 12, 14, and 16. So we've got the right number of valence electrons in the structure, and we can verify that each atom now has an octet of valence electrons. Carbon still had the octet that we gave it from the start. Okay, so each atom now has an octet, and so that must be the right structure. Just one more time off to the side over here. The Lewis structure for carbon dioxide. There it is. Okay, so I would like for you to attempt some of the following problems here. Let's see, some of these are ions, which I don't want you to have to deal with. But I think now you could attempt this one, and you can attempt this one and this one. Okay. I want to add in one more that's not on the page, off to the side here. I want you to attempt actually a couple more. Let's change this one to NH3, and let's do one more off to the side. And what can we do? What can we do? I think that's enough. Try those 4, okay? And then you can check your work on the in the document that I'll post for you guys in the Google Drive.